Hello everyone. In this video we will talk about mirrors and lenses. We'll start with plane mirrors and then move on to curved surfaces, curved mirrors, and then lenses. So we start with plane mirrors. So let's look at this figure over here. This figure is actually showing us how an image is formed when an object is placed in front of a plane mirror. So this black line over here with this blue sort of wavy outline, that represents our mirror, and the arrow, this arrow represents our object. And whenever we want to form an image in ray optics, we'll always start by constructing two rays of light that either will appear to come from a point or will appear to converge to a point, giving us an image. So for example, over here, this object, when it's placed in front of the mirror, if I take two rays of light, the first one, which is parallel to the normal to the mirror, then after reflection, that ray of light just goes straight back. And then if I consider a second ray of light, which is at a certain angle, at an angle over here like this, let me draw a normal line at this point, then laws of reflection tell us this angle of incidence, theta I, must be equal to the angle of refraction or reflection, theta R. And so after reflection, these two rays of light seem like they're coming from this point over here, and hence that point is the image of the object, right? And by extension, we can say that this entire object will then form an image right over here. Okay, so this is how images are formed with plane mirrors. There are some properties of plane mirrors that we should focus on over here. So it turns out that virtual images, that is images formed behind the mirror, are what are formed with a plane mirror. And as you can see, if I just constructed the geometric distance between the object and the mirror, then it would be exactly the same as the geometric distance between the image and the mirror. So the object distance is equal to the image distance. And also, as you can see, the height of the object is exactly the same as the height of the image. So these are some properties of images formed by plane mirrors. There's an additional quantity that we would want to know. We will call it magnification. Okay, magnification, and what this magnification refers to is relative to the object, how large is the image. So it's going to be image size divided by object size, right? So that's the definition of magnification. And oftentimes in the kind of ray optics we will do that, this ratio will also look like image size over object size will also look like image distance over object distance. Okay, so this is something that we have to know. Image distance over object distance. And for reasons that will become clearer, then the magnification really is defined as the negative of the image distance over object distance. So in terms of variables, we can write the magnification m is equal to image size over object size, and oftentimes we'll refer to the image distance as v and object distance as u. So this is really the formula that we are after. In case of a plane mirror, it turns out that this m is equal to 1. Okay, and how do we see that? Well, image size and object size are exactly the same, equal to each other, so I over O must be equal to 1. And V over U is, in the case of a plane mirror, -1, because V is equal to negative U. So if you look at it, then this is the object distance, right? Object distance, and that is the image distance. And as you can tell in this picture, they are when you want to figure them out, you have to go in opposite directions from the mirror. So that's the object distance. This is the image distance. So there is a relative negative sign between them. So for a plane mirror, it's always true that m is equal to -1. Okay, so now let's talk about what happens with refraction at plane surfaces. And in order to do that, let's use this picture that I have over here. We're just going to construct the rays of light from that picture. So again, I have this time I have a slab of glass, right? Neither of the two sides are shiny or silvered. which means that light can pass through this slab of glass. So then what will happen is I can draw a ray of light to do this. I can draw a ray of light that goes like this. So this is my first arrow, ray of light. And as you can tell, because I drew this ray of light as a normal line, it's going to pass undeviated, and it's going to keep going undeviated like this, right? So that's because of the fact that the angle of incidence is equal to 0 degrees, angle of refraction must also be 0 degrees. If you remember Snell's law tells you that n1 sine theta 1 is equal to n2 sine theta 2. And in the special case that theta 1 is 0, theta 2 must be 0 to satisfy this equation. And that's what we are seeing over here. Now let's consider another ray of light that is going at a certain angle with the normal line. So that's my normal line, and so it's going at an angle. And now this ray of light is going from air. So we will consider this medium to be air. Let's say this is glass and this is air again, right? So because this is now going in, initially this ray of light was incident at a certain angle, which is non-zero, and it is going from air to glass, that is rarer to a denser medium, it's going to move closer to the normal. So the refracted ray would do that. Okay, and now we will have a second normal line over here. So this angle of incidence is now smaller, but this time the ray of light is actually moving from denser to rarer medium, which means it's going to move away from the normal. And it turns out that these two angles, the initial angle here, theta, let's call it theta air, must be equal to this angle theta air as well. Okay, so what we will see really is just, if I trace this line back, we'll see an image that is formed somewhere over here. Okay, so it will look like this. If this was some object that is on the other side, it would kind of look like it's closer to the surface of the glass than the actual object. Okay, we have kind of seen this kind of phenomenon is in what we called real versus apparent depth. Okay, so that's what happens with ray diagrams, at least for the part with mirrors. So now we will move on and start talking about more stuff. So first thing that we're going to talk about is what happens if we have a combination of two mirrors. So here we will talk about combination of mirrors. We have in this picture an arrangement where there are two plane mirrors, mirror 1 and mirror 2, that have been kept at an angle relative to each other. And then we have a point source P that is kept in front of both of the two mirrors, such that there's a person's eye located right here that is looking at the images that are formed in this set of combined mirrors. So when a situation like this is set up, then the object P, which is the real object, will form first virtual images on each of the mirrors to which it is located in front. So for instance, this object P is located in front of mirror 1 in this part of the picture. So it's going to form an image P1 prime right behind mirror 1. And similarly, if I look at the extended part of mirror 2 shown by this dashed line, the object P is in front of this mirror. So it's going to form an image behind the mirror at P2 prime. And each of these images are going to obey the rules of reflection. So particularly when an image is formed by a plane mirror, the image distance and object distance are exactly equal to each other. So in this case, this distance, the perpendicular distance from the mirror to the point P, will be equal to the perpendicular distance from mirror 1 to point P1 prime. And similarly, the perpendicular distance from P to mirror 2 will be equal to the perpendicular distance from mirror 2 to P2 prime. Okay, but now there's one more catch. So if you look at P1 prime, then this point, which is really the virtual image of P on mirror 1, turns out that it is in front of mirror 2. So it'll form a virtual object for mirror 2. and it will form another image, which is this P12 double prime. Okay. On the other hand, P2 prime, notice that P2 prime is behind both mirror 1 and mirror 2. This shaded area over here is behind both those mirrors. Since P2 prime is a virtual object that is behind both mirrors, there's no way that it can form an image. So this process of forming images will just stop with this P12 prime. So there are a total of 3 images. Now you can see that this number of images will actually depend on how many mirrors there are in this combination of mirrors. Okay, so this is generally the idea, the conceptual idea behind formation of images by combination of mirrors. We'll go and do a problem in a very simplified situation. So we'll take a situation where there are 2 plane mirrors that are placed parallel to each other such that they are 1 mirror apart. A point object is placed 0.4 meters from the left mirror. Find the location of the first 4 images on the mirrors. So let's take a look at how we can do this. So in this picture, notice that this is the sort of the reflecting or the grayed out side of the mirror. That is, it's not this side. That side is not reflecting. This is the side that is reflecting. And similarly, the other mirror also has a similar reflecting surface that is arranged like this. And I'm placing an object P right in between the 2 mirrors. So as you can tell, the first image of this, let's call this mirror 1, let's call this mirror 2. So P will form P1 prime, which will be somewhere over here. And that P1 prime will be at a distance 0.4 meters from mirror 1. And similarly, P will form an image somewhere over here, which we will call P2 prime. And P2 prime will be at a distance 0.6 meters from the second mirror. Okay, but P1 prime is now in front of mirror 2 and P2 prime is in front of mirror 1. So each of these will now get reflected. So we will find 2 more images. So the image of P1 prime on 2 will form somewhere over here. And note that the distance from P1 prime to 2 is 1 meter plus 0.4 meters, so 1.4 meters. So somewhere over here at a distance of 1.4 meters, we will find the image of P1 prime on 2. So we'll name it P2 1 prime. Okay, this naming convention, it's not very important how you name it, as long as you remember that this P21 prime is really an image of P1 prime. And similarly, P2 prime will form an image on the other side as well, but P2 prime is at a distance 1.6 meters from mirror 1. So it's going to form an image that would look like P1 2 prime, and that's going to be at a distance of 1.6 meters behind mirror 1. Okay, now because P12 prime and P21 prime are both in front of the opposite mirror, so for instance P12 prime is in front of mirror 2 while P21 prime is in front of mirror 1, they will again form further images further away, right? And this process is going to keep going ad infinitum. But we were asked to only find the first 4 images, and that's what we have done. So this is the first image, second image, and you can call this one the third image and the fourth image. So those are our 4 images for this problem. So we will now talk about spherical mirrors. So spherical mirrors are basically made from a surface that is curved. So if I take a sphere and then cut out a portion of that sphere between, let's say, these 2 points over here, and then silver the outer side of the sphere over here, then that will form a concave mirror. And I can alternatively also cut out the this other side, but this time silver the back side of the mirror, so that the shiny side, the reflecting side, is up front outside over here. That will be called a convex mirror. So these are the 2 kinds of mirrors that we will deal with, and it turns out that concave mirrors are often also converging mirrors because light rays converge upon reflection, generally upon reflection from a concave mirror. And generally the image from a concave mirror can be real and it can be cast on a screen. What about convex mirrors? Convex mirrors, light rays diverge after reflection, generally diverge after reflection, and the image cannot be cast on a screen. So the image in case of a convex mirror is generally a virtual image. It turns out that in some situations, even the image that a convex or a concave mirror forms can also be a virtual image. And we will see an example of that later on in this video. Moving on, if I consider a spherical mirror, so basically I've taken this arc of a circle, which is really representing part of a sphere, and I've put a point object along its axis, and the axis is really a radial line through the center of the sphere, but touches like sort of the center point of the mirror over here. And I put this red object here so you can see that now rays of light will come from this red object and get reflected. But as we look at two different rays, one ray that is closer to the axis than the other, then these two rays really, after reflection from the mirror, go and get focused at two different regions. So because of this reason, even a point object which can be sharply focused becomes blurry or becomes more sort of squished when you look at its image on a mirror. So the essential idea is that not all rays of light converge to the same point after reflection from the mirror, and this causes what is called spherical aberration. Okay. So because there is spherical aberration really happens because there are two kinds of rays. We'll call the two kinds of rays paraxial rays and peripheral rays. And paraxial and peripheral rays focus at two different regions after reflection. And in order to not deal with the complications that arise out of spherical aberrations, we are going to ignore peripheral rays for this course. So the rays that are far away from the axis and more closer to the periphery. So we're going to ignore those kind of rays, and we're only going to talk about paraxial rays, rays that are close to the axis. And what is the axis? Well, if this is my mirror, I've drawn the mirror over here with a flat surface, but it's not a flat mirror. And the reason why I've drawn it with a flat surface is because I'm mostly interested in paraxial rays, so I'm really close to the axis of the mirror. And as I'm close to the axis of the mirror kind of looks flat to me, although it's not really flat, right? So this is my curved mirror, and this is the dashed line over here that represents the principal axis, or sometimes just the axis of the mirror. Okay, and that line goes through the center of curvature of the mirror and also through a point on the mirror, which is which will be generally called the optical center of the mirror. Okay, so now let's put an object in front of this mirror. We have to figure out where the image can be formed, and in order to form the image, we always need at least two rays of light to come from one point on the object, and then after reflection we want to see what happens to those two rays of light. Now there are various different rays of light that we can construct for reflection, and these different rays follow different rules. So we will talk about the radial rays, parallel rays, and focal rays, which are going to be the main kind of different rays that we use to construct our image. But in order to do that, let's talk about two important points on the principal axis that are going to be important. So the first one is going to be the center of curvature of the mirror. So center of curvature. And what does the center of curvature represents? Remember, we created our mirror out of a sphere, right? So this mirror was created out of a sphere. The center of the sphere, we will generally refer to that as the center of curvature. Okay, and so center of curvature is that that point over there, and then the radius of curvature, of course, is the radius of the mirror itself, and that's the distance from the optical center to the center of curvature. And this one we will call R, or radius of curvature of the mirror. Okay, so that's the radius of curvature of the mirror. Great. And then there's going to be another point halfway between the center of curvature and the optical center will be the focal point or focus of the mirror. And then we will call the distance between the optical center and the focus of the mirror F, or the focal distance. And just by construction, because I put the focus right in the middle of the center of curvature and the optical center, we can tell that F is really equal to R over 2, or R is equal to 2 times F. That is, the radius of curvature is twice the focal length. So this is a formula that we will need for our future. Okay, so now let's sort of move on and try to talk about the radial rays and the parallel rays and the focal rays. So the first one will be my radial ray. So let's talk about the radial rays, and I think it's easier to do that by looking at this figure over here. So I've redrawn my arrow over here. This is my principal axis, and that's the mirror, with that being the optical center. So radial ray is a ray, this red ray of light that's coming from the tip of the arrow and going through the center of curvature, which is marked by this R. Okay, so the R is representing the fact that this is a 1 radius of curvature away from the optical center. The F is marking the fact that this is 1 focal length away from the optical center. So the rule for the radial ray says that rays passing through the center of curvature pass through the center of curvature upon reflection. So this red ray of light, once it goes through the radius of curvature, center of curvature, it's going to go hit the mirror and come backward, right? So this is in the case of a concave mirror. So this example, this particular first example over here, this is really a concave mirror. And something similar happens for a convex mirror, which we have shown over here in the bottom picture, right? So this is the picture for a convex mirror. So convex mirror, it turns out that the center of curvature and the focus, they are actually on the opposite side of the mirror when compared to the object. So let me make this a little bit smaller so that I can bring this back in here. And now you can see that this is the object, that's the mirror, and the focus and the center of curvature for the convex mirror are behind the mirror. Okay, so since it's behind the mirror, this ray of light that is coming from the object cannot actually pass through the radius of curvature or the center of curvature, because of the simple fact that when this ray of light goes and hits the mirror, it would have already hit the mirror before going any further and going and reaching the focus or the center of curvature, right? So this rule for the radial ray still holds, which is that once you consider a ray that would be hitting the center of curvature, then that ray of light would just be reflected backward, just straight back. Okay. All right, so now let's move on to the parallel ray. So what does the parallel ray do? Well, in the case of the concave mirror, the parallel ray just hits the mirror, and then after hitting it, it passes through the focus, right? Rays parallel to the axis pass through the focal point upon reflection, right? That's the second rule. In the case of convex mirrors, it's very similar, except the focus is behind the mirror, so the ray can't actually pass through the focus. It's going to appear to come from the focus. After reflection, the ray of light is going to appear to come from the focus, which is behind the convex mirror. And finally, we have focal rays. Focal rays are just the reverse variety of parallel rays. So if a ray of light was originally, for a convex mirror, was originally trying to go to the focus, then after reflection, that ray of light will become parallel to the axis, and that's in the case of a convex mirror. In the case of a concave mirror, the ray of light that is going through the focus and then hitting the mirror will then become parallel to the principal axis. Okay, now if we have any of these two rays of light, then we can construct an image of the object. So for example, in this concave mirror, you see after reflection, all three of these rays, the black, the red, and the blue, and in fact I have actually added an additional kind of ray, this blue ray. So in this case, we only talked about the radial, parallel, and focal rays, which are going to be important for us, but there's also the central ray, which after reflection just makes the same angle with the principal axis as it did before it got reflected, right? So that's our central ray, but we don't really have to bother about the central ray for now. For the mirrors, it's going to be more important for a lens. Okay, so coming back, you see that all of these different rays after reflection, they all intersect at the same point, which is this point over here, and that point is going to be our image. And as you see, this image here, that image is formed by actual interference or actual intersection of all these rays. So this is really, if I put a tiny little screen over here, you can imagine we will see an actual image of this arrow. And so this is going to be a real image, okay, real image, and you can see that the image is inverted. So our original object was straight up and down, upright. So this was the tail of the arrow, that was the head of the arrow. But now you see that the head of the arrow is, the tail of the arrow is actually above the head of the arrow, which shows you that this image has become now inverted. Okay, so inverted image. And in the case of a convex mirror on the other side, the image is actually formed behind the mirror, and it's a virtual image. Okay, and finally let us talk about what happens when a beam of parallel rays of light are incident on a mirror. So in the case of my concave mirror, if there is a beam of light that is incident parallelly on the mirror, then these rays of light will actually end up converging, but they will converge this time not on the focus itself, but they will converge on somewhere on the focal plane. So if this is my principal axis and this is the focus, then this plane will be called the focal plane, and somewhere on the focal plane these two rays of light will converge. That's in the case of a concave mirror. But in the case of a convex mirror, just the opposite will happen. So this is, now we're talking about a convex mirror, and there's a ray of parallel sort of rays of light are coming and are incident on the convex mirror. After reflection, they are going, this is a diverging mirror. So these rays of light after reflection, they're going to try to go away from each other, and as they go away from each other, they're going to appear to be diverging from somewhere on the focal plane. So if this is my principal axis and this is my focal plane, that's the focus. A plane that is passing through the focus will be the focal plane, and so somewhere on the focal plane will be the image, the virtual image of this infinitely far away object from which the parallel rays of light are coming. And so these parallel rays of light after reflection will appear to diverge from somewhere on the focal plane. Okay, so now that we have discussed the basic ideas of ray diagrams for mirrors and lenses, let's now move on and try to talk about how to do the mathematics with these sort of situations. And for that, we will try to talk about two main relationships. So we'll call them the mirror relationships, right? So there's going to be so the things that the different kinds of variables that we have learned, the first one is the focal length. Okay, F will stand for focal length, and then we will have we will call U the object distance, or sometimes this will also be S, and V will be the image distance, and sometimes this exact thing would also be called S prime. Okay, so then with this, there's one additional thing we know, that there's the radius of curvature R. Okay, so that is radius of curvature. Okay. All right, and then we know that R is equal to 2 times F, right? Radius of curvature is 2 times the focal length. And then we come to the main mirror equation. Okay, so mirror equation, and this mirror equation will be independent of which kind of mirror you're looking for, concave or convex. Concave or convex. It does not matter which kind of mirror you're going to look for, concave or convex. The mirror equation would take the form 1 over F is equal to 1 over S plus 1 over S prime. Okay? Or in terms of U and V, this is the same thing, looks like 1 over U plus 1 over V. Okay? So 1 over the focal length is equal to 1 over the object distance plus 1 over the image distance. That's our mirror equation. And it does not matter what kind of mirror this equation is for, concave or convex. It's going to be the same equation. Okay, but depending on whether it's a concave or a convex mirror, we will have some subtle differences. So for the main differences is that when I draw a mirror like this, and this is the back side of the mirror, then everything over here in front of the mirror, so this will be the front of the mirror, and that's the back of the mirror. The front of the mirror, any quantity that appears there is positive. Back of the mirror, any quantity that appears here is negative. Okay? So now remember, okay, remember from our previous pictures over here, right? The focus of a concave mirror appears in front of the mirror, which means that for a concave, so now let's make the distinctions between concave and convex. So concave, f is greater than 0, or f is positive because in front of mirror. It's an actual focus in front of the mirror, okay? And generally, the object can be, for a concave mirror, the object can be in front or behind. If it's in front, the object distance is positive. If it's behind, the object generally for a mirror always has to be positive, right? Because the object has to be in front of the mirror. If the object is behind the mirror, you will generally not see an image. On the other hand, the image can be either positive or negative because there is a possibility that the image is formed behind the mirror. Just for example, in the case of a plane mirror, the image is formed behind it. Similarly, for a concave mirror, it can also form behind it in certain situations. And then the other example is the convex mirror. And the convex mirror, f, as we saw before, f, the focal point, right? The focal point is behind the mirror. Since it's behind the mirror, that has to be a negative quantity. So f is negative, okay, behind mirror. That's the idea. Okay, so once this idea is clear to you, you will see that problem solving becomes really easy. Okay, so for example, so let's do an example. So for example, if I give you a concave mirror, f is equal to 1 meter. So these two are kind of interchangeable because I told you that the focal length is positive, the mirror must be concave. Okay? On the other hand, if I give you a convex mirror, automatically, whatever the given focal length, the focal length has to be written as a negative quantity. So f equals negative 1 meter, right? So this shows me, either of them show me that it is a convex mirror. All right, now consider an object placed 2 meters in front of either of these mirrors. Okay, so instead of drawing a ray diagram to figure out where the image is going to be, we are going to use the mirror formula. This is 1 over f equals 1 over s plus 1 over s prime. So in this case, s is equal to 2 meters. It's always in front of the mirror, so it's positive. So now let's do the algebra. We have 1 over f is equal to 1 over s plus 1 over s prime. We know f and s. We need to find s prime. So this will give us 1 over s prime is equal to 1 over f minus 1 over s. And we can simplify this to write f times s minus f, or s prime is equal to f times s divided by s minus f. And now we can plug in the numbers. S is 2 meters, f is 1 meter. So in the numerator, we have 2 times 1, which is 2. And then we would need a meter over here, divided by s minus f. S is 2, f is 1. So 2 minus 1. So 2 over 2 minus 1, which is equal to 2 meters. So that tells you that if the object is at 2 meters, the image will also be at 2 meters. Okay? This 2 meters, because it's positive, the s prime is positive, that represents that it's going to be in front of the mirror. Okay, so if I draw the picture for this situation, if this is my mirror and my object is over here, the rays of light will go like this, and maybe this is the focus over here. They're gonna do this and come back, and my picture is of course not perfect, but they're gonna basically form a virtual image over here. So this intersection will happen somewhere over here if we drew a picture following all the rules. Okay. All right. So this is my image distance for scenario, what would happen if this mirror was convex? Well, the same formula applies. The only difference is that f is now -1 meters. So this one, while this one was for concave, for convex, now we will have the same exact formula will apply. Convex will have s prime equals fs over s minus f still, but now one of them, f, is -1, so we get -2 meters in the numerator divided by s minus f. Well, s is 2 and f is -1. So if I plug that in, I'll get 2 minus -1. So that's equal to -2/3 meter. Okay, so which means that because this is negative, that means it's behind the mirror. So if I wanted to draw a picture, that picture would probably look something like this. So this is my object, right? And I know that the image will be formed -2/3 of a mirror behind it. So after reflection, this ray of light is probably trying to come back from from the focus, which is somewhere back over here. So that's one ray of light. And then the other ray of light would be something like this, I guess, which goes all the way to the center of curvature. So it goes like this, comes back like that, and so these two rays of light now appear to come from this spot, and this distance is your -2/3 meter. And so these are sort of two ways in which you can find the position of the image using this algebra. There are several different cases, and each of these different cases you can work out the result for the object distance or image distance given this formula. There's one additional quantity that we always have to remember for our mirror problems. Remember, or even lens problems. We talked about this before in the case of plane mirrors, m, which is magnification. And by definition, magnification, m, is equal to image size over object size, but it's also equal to negative of the image distance over object distance. Or if I use the notation of u and v, then it's -v over u. Okay, so let's try to see what our magnifications in these cases are. So for this first example where the mirror was a concave mirror and the object distance was 2 meters and the image distance was 2 meters. Well, let's see what the magnification is. M is equal to -s prime over s, but s prime and s are both 2 meters, so we get -1, right? So the magnification is -1. This is actually telling you that the size of the image is exactly the same because of the factor 1, but the -1 is telling you that it's opposite, it's inverted relative to the object, right? So this tells you same size but inverted. Okay, that's our idea. But now let's do it for the convex mirror. For that, m is still equal to -s prime over s, but -s prime is now positive because s prime was negative, so we get 2/3 meter, that's our s prime, divided by s, but s was equal to 2 meters. Okay, so these meters will cancel, we get 1/3. So m is equal to 1/3. This is telling you that the image size will be third of the object size, but it's going to be upright. So this is telling you upright because of the positive sign in front. So if the magnification is positive, the image is upright. If the magnification is negative, the image is inverted. So this is sort of the idea for solving problems. Okay, so this is all great. Okay, but now let's see what happens if we start moving our image or object. So if I start moving my object, okay, so our image will clearly move. What if you're asked to find the speed of the object or the speed of the image relative to the object? Okay, so how do we get to that? Well, let's try to see what the speed could mean, right? So the speed of the object. What can the speed of the object mean? Well, speed of anything, right? Speed is distance over time, or in terms of calculus, it's just dx dt. So dt time derivative of some distance. But so since we are talking about the speed of the object, this must be time derivative of the object distance. Okay, So ds dt in this case, where s is the object distance, right? So that is our object speed. Okay, this is our object speed. All right. And if now I want to talk about the speed of the image, well, speed of image, that will come from the other variable that we have, which is s prime, right? So s prime, if I take a derivative of s prime, ds prime dt, that's going to be the speed of the image. Okay, but remember that these are related to each other, right? So 1 over s plus 1 over s prime is equal to 1 over f. And what is df dt? Well, the focal length of the mirror is not changing, which means df dt is 0. Okay, so since df dt is 0, we can sort of use that to our advantage, because if df dt is 0, 1 over f is also not changing. So that means that time derivative ddt of 1 over s plus 1 over s prime is equal to 0. So then that gives us 1 over s times, um, so let's take a derivative, ddt of 1 over s plus ddt of 1 over s prime. That is equal to 0. Okay, but now let's take a derivative of this, so we get negative 1 over s squared ds dt plus, or actually another negative 1 over s prime squared ds prime dt is equal to 0. And so if I take this to the other side, then this equation then will result in the following relationship. We will find that ds prime dt is equal to s prime negative s prime squared over s squared ds dt. Okay, so this is our relationship between the image speed and the object speed. So if I make the object move at a certain speed, right, then the image will also move at a certain speed, and this is how they're related. Now we can go one step further and notice that m, the magnification, is equal to negative s prime over s, which means this factor s prime squared over s squared is just equal to the square of the magnification. So if you use that, we can transform this formula over here to this formula. This shows us that ds prime dt is equal to negative m squared ds dt, or in other words, the image speed is equal to negative the magnification squared, right? So this is the square of the magnification times the object speed. All right. So that is essentially most of the ideas that we'll need for um, our mirrors and curved mirrors, image and object and focal length and radius of curvature, etc. In a future video, we will come back and talk about lenses. Thanks for watching.